The problem is basically that we have a square, and in each corner we have a dog. Okay, so the green dot marks a dog, and so we have a dog in each corner, and each dog is running for the next dog counterclockwise. So this dog is running with a certain speed, and they are all running with the same speed, so we could say that their speed is equal to 1 meter per second. And then you could imagine that we divide this square up into different smaller squares in a grid, where each square has the width of 1 meter. And so in 1 second it will travel 1 square in the direction of the next dog. So this one would travel this way, where they are all kind of spiraling into the same point. And so this is the problem, because the question then is, how long time does it take before all the dogs are centered within the middle? We could draw away some complexity of the problem by kind of simplifying it down into certain iterations. We could break it down into certain steps. And so we could say that we count in time steps of 1 second. So each second travels 1 unit. And then what we need to do is that we need to calculate this vector, this velocity vector, which will tell us where the dog will land. So we need to basically compute a certain amount of steps. Say we could have like size n is equal to 100 or equal to 10, and then we'll calculate how much the dog would move for each step. So you can imagine that we could pull this apart into one vector, which would be the y, and one which would be the x. Okay, and so is 1, because we are taking 1 step. Well, the first thing I'd like is to compute the angle. So we need the angle between, and so we need to compute this angle to know in which direction the vector is heading. And now, if we know these two sides, well, then we can compute the angle, because this is just the arctangent of, let's see, x2 minus x1 over y2 minus y1. So this is the angle. And so we have already denoted that the angle theta is equal to arctangent of the difference in x over y. And so we could just take the sine of that. And so the length of this one right here, this one will be sine of arctangent. I will denote this as arctangent. And then I will denote this as delta x over delta y. And then inversely, this one, the y vector, will be equal to the cosine of the arctangent of delta x over delta y. And so this is how you could compute the different steps. And so we get that this is equal to sine of arctangent, and I will write out x2 over x1 over y2 minus y1, and this will be times our velocity constant divided by n. Okay, and this is just over the first iteration, because now this should be x1 over the next step. And so this will just be this again. And now this will be x2 minus this value. So this was kind of, you could notice as 0 minus x1 1 over y2 minus y1 times our vector, velocity vector divided by n. And so we need to compute this for multiple iterations, and so we could just make a sum out of this. And so we make a sum. We set k is equal to 0. And then we could write this as sine of arctangent of x2 minus And we will need to write this down also, because this will be, because this dog also moves. X2 k minus x1 k over y2 k minus y1 k. Okay, and then we will multiply this by the speed vector over n, and this will be up to n, and then obviously, because this is a kind of this where the calculus part comes in, well, then we want to know what happens if the step size goes to infinity, because it's continuous. And so we finish this off by saying limit as n goes to infinity. But then the thing is that if we draw a triangle right here, the angle that we're interested in is right here. But then to get the arctangent, well, then we also have to take the opposite over adjacent. But this time the opposite is the difference in y coordinates, and so it would be the same thing, but it would basically be flipped. So instead of taking delta x over delta y, we would take delta y over delta x. Because what you can do is that you can take the arctangent of this same thing, but now delta y will delta x, and so we flip it. And so we would instead basically compute this angle, let's denote it as gamma. And so if you add gamma and theta together, then they will be 90 degrees. And so obviously if you are right here, then you can just take 90 minus whatever this one returns, or you could just flip it for consistency. And so, okay, so if I would write this out as a computer program, then we would need to take in the positions. We would need a position of the dog 1, which would be x1, y1. Okay, so we could create a set with all these vectors. And then we need to compute, and then we denote also that the vectors change all the time. Yeah, and so we would start off by basically calculating all of these values, and then we would change all of these values by these values, and then we would reinitiate the loop. And so we would just keep doing this until we will just do this for a certain amount of iterations. Okay, so we need to define some sort of loop. And so we need to set a certain amount of steps that we want to take. So we want to set, we want to define a certain set of iterations. So I'm just going to set const n to be 10 to start with. And then for each iteration, we probably want to define some while loop later on, because we want to run this loop until it reaches the center. But the thing is, it might never reach the center, because remember, this is calculus, so it might just approach the center. So we'll have to see how we'll do about that. But for now, let's just set up a simple for loop. And I want a small, whatever, let's use a big one. Okay, and then I++. Okay, cool. So basically this will just complete our formula, just like we said. So it will take in this numbers, and then by our formula that we went through, it will then calculate the angle using the arctangent, and then it will also check if it needs to flip this by taking the 90 minus angle, in which case it will, and otherwise it will just return the array with our velocities. Okay. Okay, it seems like we're actually up and running right now, so let's just check this, that it's correctly printing out. Okay, great, so now we finally got our array of velocities for the first iteration. Now that we've defined the velocities for the first position, well, first we need, before we move the first one, we need to define
the velocities for each other one. So we need to... Okay, so what you can see is that I basically am running the loop. So I'm computing for each iteration the velocity depending on the current positions of the dogs. And then now I'm going to move each position by these velocities, and then I'm going to recompute the velocities and then redo it again and redo it again. Yeah, well, obviously if that's... Oh my god, I get it now. Oh, such a simple mistake. I had, oh man, it was supposed to be a 1. I chose the wrong index. Okay, now it's 100% working, I promise you. Yes, this is my angle. Okay, so we got 0 here. Okay, so it's super cool. So we got the first point right here. And then we got all of the other points, and we can see how the points are moving. Okay, so we got some negative position right there. I don't know if this is what we want. Probably not. Okay, so we finally got a square. This is very delightful. Very delightful indeed. So we have cosine of 0 times 1 divided by 100. So we should have 0.01. Okay, that seems correct. Oh wait, we divide by 0. That's dangerous. Oh wait, it takes in the angle in radians. Oh wait a second. There, you see it? They are spiraling towards the center. Only that the center is misplaced in this case for some reason, but they are spiraling close to the center. Okay, that's pretty interesting. Yeah, let's disable this hook. And instead I'm going to call the function draw figure. Because it should be spiraling in towards the center, but or somehow it doesn't seem like it's... Oh man. Oh, I messed up big time. Dude, I'm too lazy sometimes. It's just a simple mistake that gets you. Oh, it's returning negative value. Yeah, well, the derivative can absolutely be negative. But the position should never be negative. Yes, it's working properly. Okay, that's reassuring, but at the same time not, because then that leaves me more clueless to why it's not working. I will see. There are some silly errors, but I think I'm getting to record it. I think I'm really close. I just think I have to figure this part out, and then I think I'm heading in the right direction. I think I can actually solve this problem. So that's really exciting. And yeah, I'll see you tomorrow.
Okay, so I know it's late and I've got Swedish exam tomorrow, but I figured it out. I know why my code wasn't working. Previously, we had the point here, point 2, chasing point 3, and point 3 was moving with a constant velocity towards point 4, which was stationary, so it was moving like a straight line. And then point 2 was chasing point 3, and so it was moving kind of like a curve that looked like this. And then point 1 was chasing point 2, and so it was going a bit like this, okay? I don't know, looked something like this. And so all these 3 points converged to this point 4 at 10, 10. And see, this is where the problem emerged, because right as the second point, you see there's a certain level where the second point reaches where the y-coordinate of the second point is bigger than the y-coordinate of the first point, equal to theta. But now point 2 has moved above point 1 because the y-coordinate is bigger. You see, the x-coordinate doesn't matter in this case because the x-coordinate is always, because point 2 is always to the right of point 1, but the y-coordinate changes because you see now point 1 is down here and point 2 is up here, and so now the triangle that we want to draw, because we want to draw this new line, looks like this, and the angle we want is this angle. Remember, because this was gamma, so the problem was that I was computing gamma, because the new angle that we want is the theta, which it will be instead the delta y over delta x, and so the new formula becomes the arctangent of the delta y over the delta x. But if you remember, I rewrote this as 90 minus arctangent because these two had to add up to 90 degrees because it's a right triangle. And so all I should have to do is to flip the values, the Boolean value of the parameter in my function.
Okay, so I have to set up some borders for the different kind of like when it passes between the different quadrants, because I don't, otherwise I will divide by 0, which is what I don't want, so I need to check for that. So I have two particular cases, and those two cases are when there is no value over y, when the y is equal to 0, or the y difference is equal to 0, delta y is 0, but the delta x is not equal to 0, because then in that case we can't divide delta x over delta y, because then we will divide by 0, so we have to check for that. Wow, okay, look. This is actually kind of interesting, because it seems like it actually kind of works when I put in this limit right here. Okay, so the thing is that it returns a velocity, but it's 0.2, but it really should be negative 0.2, so I need to go through it step by step, and I need to find exactly where it goes wrong. I don't know, but it seems like we have to multiply both values by a negative, so I'm just going to do that. It seems like there's gone something wrong with the sign. So let's just try to take this code, move it down, and then okay. Let's try again. Yes, this seems correct. Okay, let's rerun all the tests. Straight down, yes. Right, yes. Left, yes. Up, yes. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay, so it seems like all directions seem to be working properly now, so let's try once again. Okay, cool. Nice. Okay, things look good. Now this is the point where we're supposed to switch, and it looks like it properly made the switch. Now it's moving upwards instead. This one is still increasing. This one is chasing this one. And this one is chasing this one. And they should all converge to 10. And it looks like it does. So it looks like the program should be working properly. So now let's try to introduce the fourth velocity if I'm brave enough. Okay, pray to God now that works properly first try. I'm also going to increase the amount of iterations. Now they should all converge to 5, 5. Oh my god. Oh my. Hey. Whoa, okay. Do you see this? Take a look at this. Oh my god. It's... Look, it's reaching 5, 5. It seems like it's actually working. Oh my god. This... Okay, so it seems like it's doing the actual spirals. Now I need to get the animation properly working, and then I know that it probably is correct. Oh my god, look at this. This is perfection. Look, it's all in the center. Oh my god. Oh my god. Did you see that? Oh my god. Wow. Okay, dude. I need to get the camera. Okay. So this is very exciting. There's still a lot of jargon that I have to clean up. But you can see that it's actually like working. You can see that it forms these absolutely beautiful spirals, which is what I have been working for. And now all I have to do is to make sure that I can properly adjust my variables so that the user can adjust the variables, and then I will get the final answer to the question, which is how long it takes for the dogs to come to the center. Okay, let me just put on my glasses and finish this. Okay, so I got a lot more to set up. So I'm finally done with the essence of it. It was like seriously hard to set up like the proper velocities. Let's just try to see how hard I can push this. Let's do 1,000. Oh man, it's actually working. Computing very nicely. Exact computations. Okay, I'm going to try to push this as much as I can, but pushing it up to 10,000 and pushing the velocity up to 10 so that it doesn't take forever. Oh man, dude, it's actually running. This is actually super impressive. Okay, let's bump its speed up to 10,000 and to 1000. Oh, okay, shit, I'm gonna regret this, ain't I? Dude, like, how is this like even... Oh my god. Wow. Okay, so it seems like it's actually kind of converging in a way. Wow, dude, did you see that? Did you seriously see that, dude? What the hell? Wow, look at that. Like, this is like mathematical art. Dude, see the shape that it follows? God damn, there's gotta be some special function, or I am not aware of what math. There is probably some crazy function to describe this very shape. Wow. Oh shit. So I should really go to sleep, but I just want to play around a bit because it forms these really interesting shapes and I want to see how they change. And by the way, if it's not clear, these lines are just the lines between this point and that point. So it's just this one is chasing this one, and so it draws one line over there and one line over there, and then it moves. And then you can also see the way it moves that way. I'm just watching this over and over again. Okay, I just realized why time was kind of off. You see, this is the time it takes per step, and this is how many steps there are. And so it will take 9.762 seconds, which makes sense because the path is 9.762 meters and I'm traveling with speed of 1 meter per second. However, something was really effed up, but now I realized that it's because this is 0.01 seconds and I was previously counting in milliseconds, so things were going 1,000 times too fast and it was passing the index of the array. However, that should be an easy fix. And the animation is back on. We're back on, boys. It's running. But more importantly, it should be more appropriate this time. Now it should be like actually kind of working. You see, because now it's more accurate, because now they are really traveling at the speed of 1 meters per second, which previously weren't. It was kind of like a bit randomized, but now the time is set correctly, even though I'm not using a request animation frame, which might not be optimized. You can see that it's a bit laggy, but I think the important thing is that it's rendering with the correct variable, so that's very nice. Now I just gotta add another stopping condition, so I'll just check. Okay, this looks really good because now we actually have reproducible results. That's why I changed the timer, because it was always like fluctuating. And so obviously when the main question is how long it takes and you get different answers over every iteration, you can't really trust it. But it seems like we are basically getting the exact same answer every time. Yeah, pretty much. I mean, like, it very rarely changes actually. 3, 4, 8. Yeah, wow, okay, yeah. So it seems super accurate actually, so that's really reassuring. Okay, so this seems to be about the problem that I've been working on, which is the time that it takes. And you can see that you can do a lot of different shapes and a lot of different polygons. So I'd probably like to work with that and try how that would work. Yeah, but I want to know what the answer is. At least for the square case. Okay, Mohannes, please show me your solution. Oh, yeah, okay, so we have done the nice mathematical solution. And the length will be equal to my famous 9.7. Oh, well, that depends on the square size, obviously. What is the sum of the distance traveled by each power an infinite period of time? Yeah, also, well, the thing is that oh, well, there might be a thing, because I said, wait a minute. Because you see, I said that the points were at the center if the distance between them were less than 0.1, but you know, that they don't really have to reach one. I mean, like, they could technically go on forever. I just set that point for myself, and so in that case, it technically would never reach. Huh. How much does the answer change then? If I change it back to the values that I was previously using. Let's see. Oh, come on, move slightly faster, dogs. Oh man, yeah. Tension is rising. Okay, so it's actually changed the answer by a bit. And so, yeah, but In that case, then the problem would probably kind of be impossible to solve if it was for the time. 1, 2, 3, 4 of unit side length if the length is 1. So it should travel 1/5. 1 is equal to 2, 3, no, 1. It should be 1. No, the length should be 1. What happens if I set the limit like really low? What happens if I do like 0.01 and 0.01? Oh, it seems to be converging to 1. Oh my god, okay, that's so cool. Okay. So the answer... Oh, man. Oh, I missed that. Oh, shit. So, that's 0.9766. That wasn't actually the factor. That was just like a side effect of... well, the fact that I cancel out early. The question really was because, you know, they move less and less over each iteration. Wow, okay, so I found the answer to the question.
Now, it was a while ago, but I was thinking that I should come back to this project and finish it up a bit, make it a bit more stylish. I thought I was going to add a chakra eye to it, and then so I can upload this video so you can watch it. So I guess I'll just show you me making this actually user-friendly and pretty. So what I've added right now on screen is basically a start button. So I click start and then the animation just restarts. And then the point is that you're going to be able to adjust these variables, and then you're going to see how the time changes and stuff like that. And you're also going to be able to do some cool shit. So yeah, let's do that. Okay, yes, so I finished the user interface, so I thought I'd show you. So very quickly, this is where you come up, right where you enter the URL. So you can choose how many steps you want to render, which is basically the amount of iterations per loop. So the more accurate, but also more computer intensive. And then there's velocity, which is just the speed in which the dogs are running. And so you can set this up. So I could do something. Yeah, I could do 1000, and I could do 0.5 meters per second. And now the dogs ran, and we said it took them about 2016 milliseconds, and they ran about a meter.
And if I were to increase the step size or the number of iterations, then we see that the time it took slightly changed to 2 seconds, which is actually more accurate because the answer is actually exactly 2 seconds. And we can then do some cool configurations. So we could, for example, show an arrow. So if I slow it down a bit, then you can see that it shows an arrow, kind of like a velocity vector, which points to the direction in which the dog is running, or the target on which each dog is running towards. It can also do show path, and then it basically draws small circles a lot of times to kind of plot out the entire path of each dog. And this is the actual pursuit curve. And then we could select both show arrow and show path, and then we will get this really neat shape. Very cool. And if we slow it down a bit, then we get something truly awesome. Something like this. Very nice looking. What we could do is that we could do one slow one like this. We could run multiple at the same time. Then we could run one right here. So we get multiple animations on top of each other, and we get something really beautiful. The length of the square is 1 meter. I tried to make a parameter so one could adjust that here, but it was kind of buggy. And also, the step size kind of breaks if you go under less than 1000. So if you try something like 500, then it will. No, okay, it worked this time. But if I deselect these two, yeah, okay, now it's really buggy. So try to stay above 1000. And then I also added some links. There's this article. I haven't actually read this one, but I thought it might be interesting for some. I didn't read any literature before heading on to this project. And then I have a link to my GitHub repo. So yeah, please play around. It's super fun. See what absolutely beautiful mathematical art you can do. So, oh shit, broke something. Oh god. It's pretty cool. So see what awesome mathematical shapes you can do. The URL is 4dogproblem.net app. I put a link in the description, so just click on that, and yeah, have fun.